My experience of doing research is that it has to be done in teams. So you're going to meet the team tonight, and I just want to say a huge thank you, because this could not be done anywhere other than at 90 Sloane Street when we first started. And Michael actually took a huge risk, I think. And it's not been easy. Can you hear me now? Is that better? Is that better now? Yeah, so I was just going to say that when you do research, it's never done on your own, and you always do it in a team. And when we started this project, we couldn't really have done it anywhere else other than at 90 Sloane Street, because Michael's put a lot into this project, and together with his colleagues, Tim Lyons, Sarah Kayat, and Ben Harper, we owe them a great debt, because they let us have a go at trying to introduce whole genomes into primary care. And then the rest of the team, and we've got a stellar team now at the Genetics Centre. We've all worked together for many years. You're going to meet them shortly. Lucy Side, my colleague, is going to introduce the team as they speak. And each of us is going to speak for a very short time, but on different aspects of the project. So what's the project about? Well, the first thing is that 20 years ago, the whole genome code was elucidated. So if you imagine that I just scrape off a few skin cells here from my hand, and then it heals, you have to copy the whole of the human genome code to heal it. And that's got 3 billion letters in it that you've inherited from each parent. So you can imagine that often things go wrong, and you can actually inherit faults in the genome code, and that actually can affect your health. So 20 years ago, we had the code of the human genome. And what can we now do with it 20 years later? Well, the first thing is that we can use it to design new drug treatments, and it can actually affect how drugs work, as you'll see later in the talk. And also, it's going to be absolutely dynamic for next generation health screening, and that's what this is all about, the next generation health screen at 90 Sloane Street. The other thing is that now that we've gone through the process and we've learned a lot of lessons along the way, and that's why this evening's happening, we're now ready to work with partners in the room, both specialists and other GPs, so that when you do your health screen, the question is, do you also want to introduce genomics into it? And the team want to help you to do that. And as Michael mentioned, we're actually trying to reduce mortality, to save lives. You know, you don't want to get people having cancers, early heart disease at a very young age that could shorten their life and have an impact on their lives and their lives of their families. So what we do in the project is we take a blood sample, so it's in your genetic makeup, and what is whole genome sequencing? They actually sequence up all of the letters of the genome that I just talked about. But we don't yet know, if you imagine it's like the book of life, and in there, if each chapter was a gene, there's about 22,000 chapters. But we don't know what they all do yet. So what we've done with Veritas Genetics, that do the whole genome screening, the sequencing, is that we ask them to report things that are only actionable, so only things that we can do something about. So we're not reporting on dementia genes, Parkinson's, susceptibility genes, because we can't yet do something about that. If a drug came along tomorrow that could prevent something like Parkinson's, we would unblind the data and then start reporting it. So we're only trying to do things that will help. We're not trying to do medicine that find things that won't make a difference. The other thing is that for example, if you've had relatives that have had a cancer, sometimes cancer tumours, their actual lump of the cancer, is sequenced by their cancer specialist. And that's called somatic sequencing, so it's only the genome within the cancer itself. Whereas what we're talking about here is in the germline. So in other words, it's in your genetic makeup that you're actually born with. And there are two types of genetic alterations that we have to think about. Some are not so common. So if you imagine in this room, there's about 200 people. About one of you might have an alteration like the actress Angelina Jolie had. So she had a genetic alteration in the gene, the BRCA1, the breast cancer 1 gene. So what does that mean? That means in her breast cancer 1 chapter, one of the words was misspelt, a bit of it was missing. However, there are some groups where these alterations are more common. So if you were all Ashkenazi Jewish sitting here, 1 in 40 of you would have one of these. But they're still not so common. And then there are other alterations. If you sequence somebody's whole genome, they're very common alterations. They're just variants in the genome. And all of us have them in this room. But we could actually already type you for some of those. And certainly if we did your whole genome, we'd know what they were. And these are called SNPs, or single nucleotide polymorphisms. They're variants in the genome, and each one doesn't have a very high risk. But it's like a pack of cards. Each one gives you a certain score, and you get an overall score of risk. And so we can now pull out the top 20% of people in the room. Later on in the talk, I'll give a talk about research and what we're doing, particularly with these variants, because it's at the very new area of research. At the moment, they're not in clinical care yet, but I think they're really coming. It's the oncoming train that's coming. So, for example, in prostate cancer, a lot of the work that we've done across the world, we've worked with many groups internationally to try to find out what these common variants are. And if we imagine we lined you all up by height in a field, we now know that if we actually took a blood sample from you and typed you for 260 variations across the letters of the genome, that we could find the person at the top 1 in 100 in the room, the top 1%, and they'd have 11 times the risk of getting prostate cancer to the average of the room. And we can already do this test. What we need to do in research is to find out what then to do about it. And the other thing that's important is with these common variants, if we could find the top 20%, so the top 1 in 5 risk in the room, they actually have on the current genetic modelling about 80% of the cancer cases that might occur in the room. So it's a way of concentrating your screening to find more numbers of cases of cancer, particularly in prostate cancer. This type of work is going on now. So we thought that the whole genome screening, what would it do in the future? What's the future going to look like? Because at the moment, it is moderately costly to do it. We only know about 566 actionable genes at the moment, but more will come along. And also the question is, how would you show that data? Say you're going to a doctor, and there may come a day when you have it on your smartphone, for example, and if you go to the doctor, you'll say, this is my genome. If you're going to give me this drug, then does this fit? Am I more likely to get side effects? So it actually may totally affect how we do healthcare. And this is the team that we've amassed together. It's a very strong team. We're not terribly ancient, hopefully, but we have 175 years of experience between all of us. And we also have experts in psychology. The bottom right is Liz Bancroft. She leads on our psychosocial studies, a research fellow, and then the administrative team, and 2 trainees, one a genetic associate and one an MSc student, and they're both here tonight. So I hope you feel that we've done this very responsibly. We're trying to iron out what the potential pitfalls were with doing whole genome, and also try and find out the pitfalls so that we can streamline it and make it good for healthcare and introduce it into the NHS eventually. We're a bit of a way off that, but we already have discussions with NHS England about this. So now I'm going to hand over to Lucy, who's going to chair some of the sessions showing you some results.
Thank you, Ros. So I'd like to introduce Dr. Gabriella Pichot, who's going to give the next talk. Gabby is a consultant geneticist at 90S and has also practiced in oncology for many years. And Ros and Gabby and I have worked together for many years because we're all particularly interested in genes that increase cancer risk and how we can look after those families. So, Gabby, the floor is yours.
Can you hear me all right?
Yes.
So I would like to share with you the findings in the first 50 patients that had whole genome screening with regard to high and moderate cancer risk genes. First of all, I'd like to emphasize again that we had only actionable genes reported, and actionable also means that we know what the cancer risks are that are associated with a fault in these genes. And that's very important because the risk level will determine what we recommend for management. The second thing is whole genome screening doesn't pick up in the known cancer risk genes all the faults. For instance, the BRCA gene, that's the gene where Angelina Jolie has a fault. That's the most common genetic fault that we find in high-risk breast and ovarian cancer families. Whole genome screening only picks up deletions or omissions of letter of up to 10. If it's larger, it doesn't. And 4 to 28% of families with BRCA faults have actually a deletion. So we didn't want to miss these. So we had, as a backup, we did clinical gene panels at Invitae, 84 cancer genes. What Invitae also reports, and Veritas doesn't report, are these so-called variants of unknown significance, where we don't actually know whether they are disease-causing or harmless. Most of the variants of unknown significance turn out to be harmless, but some of them turn out to be actually increasing the cancer risk. Now, I'm only talking about the results with regard, what did we find in these 50 genes, in these 50 patients? We found faults in 7 moderate or high-risk cancer genes. We did find faults in 3 breast cancer high-risk and moderate genes, PALB2, BARD1, and BRCA. We found faults in genes that cause an increased risk of kidney cancer, and we found faults in 2 genes that cause an increased risk of colon cancer. So to give you an idea what this means for a patient where we find something like that, let me give you an example. We found a fault in a gene called MSH2, and this causes what we call Lynch syndrome. Lynch syndrome is the most common inheritable bowel syndrome, but it also causes a high risk of endometrial or womb cancer and ovarian cancer in females, and besides colorectal cancer, an increased risk in upper GI and urinary tract cancer. So this particular patient, and we have anonymized this pedigree for confidentiality, had colon cancer at a young age, at 32, and kidney cancer at 40. So what are the approximate lifetime risks with an MSH2 mutation? Colorectal is 51%. This patient already had colon cancer, but he, of course, has quite a bit of remaining colon, and he has a remaining risk due to his age of 46%. That's quite substantial. The population lifetime risk in the UK is around 6% for colon cancer. Upper GI, 20%, that's quite increased as well. It's usually 2 to 3%. Ureter and kidney, 18%. Urinary bladder, 13%. Brain, 8%. Prostate, 24%. So you see, these are hefty increases. So what does that mean for the patient himself and then also for the family? What are the implications? These patients had polyps in the last 3 colonoscopies. So usually you recommend every 2-year a colonoscopy for a patient with a Lynch syndrome. Here we recommended, of course, because of the polyps, that he should have yearly colonoscopies. Because of the increased upper GI cancer risk, should have a gastroscopy and the testing of Helicobacter pylori. That's a bacterium known to cause gastric cancer, sporadic one, just to eliminate that problem. Then chemoprevention with 300 milligrams of aspirin, prostate screening with this prostate-specific antigen, and yearly abdominal ultrasound. So you see there is a host of management options available for these patients now that we know he has such an increased risk. Because this patient, you might remember that he didn't have any sort of family history. Most Lynch patients have a lot of family history. He didn't. But it's entirely possible, but sometimes a fault starts in a patient newly at the embryonal stage. So first of all, to establish this, because the patient also has siblings and he has 3 children, the first step is to test the parents and see whether he has inherited it from one of his parents. The second point, also important, is to test his wife, because if each parent has a fault in one of the mismatch repair genes which cause Lynch, then there can be, the children are at risk actually for quite a few tumors, colon cancers, leukemias and other things, so that's quite important to know. The second patient had a BRCA1 mutation, the same mutation that Angelina Jolie has, the high risk and breast and ovarian cancer gene. What are the lifetime risks for female? They have a very high risk of breast cancer, 50 to 85%. The male breast cancer in BRCA1 is only slightly elevated. Ovarian cancer risk, again, very, very substantially with 40 to 60%, and prostate cancer about 20%. So this patient has a sister who had breast cancer quite a while ago and died. And nobody at the time when she had that was thinking, because it was just about possible to test for BRCA, to suggest to test her. So then came our patient and was tested, and his sister had ovarian cancer, was tested as well, and has the fault as well. So what does that mean again now for the patient and the family? For the patient, you've seen his only increased risk is the prostate cancer risk, and therefore he has screening with the prostate-specific antigen. That's a blood draw once a year. In the family, test the sisters or, of course, the children of the sister who has died at the age of 30, and inform both sides of the family about this result, because most BRCA faults, the overwhelming majority, in fact, are inherited from one patient. So it's quite important that the family is informed about the possibility of genetic counseling and testing. I think.
Thank you, Gabby. So we realised as we went along with this project that although we were particularly interested in cancer susceptibility, we were revealing lots of other conditions as in our whole genome sequencing. And we've talked a little bit about cardiac susceptibility, but we also realised increasingly we were picking up carriers for recessively inherited conditions. And we're delighted that Tessa Humphrey came on board with us, because she has a particular interest as a consultant geneticist in inherited cardiac disease and also in fetal and reproductive medicine. So Tessa's going to talk to us about that next. Thank you, Tessa.
Ooh, are we? Oh, I was going to say, I'm not going to talk about that. That would be a disaster. Right. So, carrier screening, preparing for a pregnancy. We've medicalized pregnancy really beyond possibility now. So let's continue. Let's have it totally as a medical problem now. So, carrier screening, the ultimate test to prevent disease. And the real problem at the moment is that actually you have to have an affected child before you can pick up a lot of these problems. 1 in 300 to 1 in 400 people at birth are affected by a recessively inherited disease. That can be one of the ones on the autosomes, you know, the chromosomes 1 to 22, or it can be on the X chromosome. And if you remember, women have 2 X chromosomes, so they're protected if they have a mistake on their X chromosomes, but the poor chaps, they don't do so well. So most of these diseases are life-threatening and severe. So who would choose to have a child with such a major disadvantage in life? I went into genetics partly because having been a paediatrician, I had watched children die. I was working on the liver unit at King's, and it really was absolutely gruesome. So can we prevent these terrible diseases? So in the past, all we could take a family history. And as I said, if you, with these recessive diseases, the X-linked ones, you might have a family history, such as something like Duchenne muscular dystrophy. But actually, otherwise you had to wait to have one affected child. So you could, and also we know that people who marry their cousins, and 60% of people in Saudi Arabia marry their first cousins. And that's really disastrous as far as genetics is concerned. So how do you test? How do you do this test? What do you do? Do you get eggs and sperm? And, no, that's all far too complicated. So we can either test both of a couple, so you can take the man and the woman, and you put them both through a genetic test. Or, if you're feeling a bit mean, you can actually just test the woman, and if you find anything, you can actually then test the man for any of the diseases. It's probably best to test them together because actually it's probably cheaper to test both of them together than it is each of them individually. And we all have at least 2 to 3 recessive diseases. And so when you get the results, you have to make sure that people aren't worried about what you find, because actually you don't want them to then think, oh God, they're going to get a problem just because they're a carrier. We are all carriers. None of us are perfect. Most of us don't know what we're hiding at the present time. So what do we test? We've already heard that we have 20,000 genes, and a lot of them don't cause recessive diseases. We don't know what a lot of those do at the present time. And that is always hugely important to remember. We are not picking up everything. And different companies offer different tests, and different diseases are tested for. So that's a little bit of a problem, because you don't quite know what you're actually getting. So you could just offer the test, and you just take the blood and you send it off, and you hope that it's all going to come back normal and all will be absolutely fine. But it is the interpretation of the result which actually is difficult, because we have to know what is tested for and what is not tested. And unless you have actually got a feel of what is involved with the diseases they're looking at, it is actually tricky to just do it without someone talking to the patient before and after the test. So, whoops, the next one is not. So if we examine what are the tests, what are we looking for? So we heard a little bit about a single mistake within the gene, and that is the easy thing. And those single mistakes within the gene, we're looking at mistakes in these things called the exons, and then you make a protein down here, and that's really leading to a mistake within the protein. So we're fundamentally looking for single mistakes within that. But we've already heard in the BRCA1 gene there are missing bits or extra bits, and this is missed by next-generation sequencing. And there are a few important diseases. Somebody might have heard of spinal muscular atrophy or congenital adrenal hyperplasia, which you are going to miss a lot of the time because they are associated with deletions. So we are missing those diseases unless you add on extra information. And we can easily do that, and that's actually now very straightforward, but you do need to have a little something added on. So what does it miss? Well, nobody can guarantee we're going to be normal. Do we even know what normality is? I don't think we do. How many of you are normal? I don't think I am. But maybe, there's someone who's normal. That's marvellous. I don't think most of us can claim complete normality. I always worry about, I have patients and they have deep psychological tests. Thank God no one's done that on me. I would be very depressed by that. But anyway. Now, I digress. So, as far as getting a normal baby, a lot of these conditions we see, and I do a lot of prenatal diagnosis in various different hospitals, and lots of things just start in that baby. We are going to miss that, and we still cannot pick that up. So we're not guaranteeing normality. And this is not a chromosome test, and my obstetric colleagues who I work with day in, day out, still have got a muddle between a chromosome test, which is looking at great chunks of material missing or extra, and a single mistake. And we're not looking at whole chromosomes. And there are still diseases that we can't look at because we don't know what the underlying cause is. So we're not examining everything, and on average we look at about 400 genes, but it is a huge, huge step forward from what we have had before. And I think now, to start with, I was very skeptical about this testing, but I really believe now that it is really worth doing. It's certainly not on the NHS at the present time, but there are all these different tests out there. But I think you have to be a little bit cautious about the cheap ones, because they are not potentially looking at very much. But I think it's a really, really interesting new field, and certainly something that I would be recommending undertaking. So and the next other half, where I work at the Brompton and at St George's, is on cardiac genetics. And this is really staying alive. This is, we've got past that baby bit, and we're absolutely now, we're going ahead and we're alive. But we've got to remember 6% of people die of a cardiac arrest. Now, for a lot of people, your heart has to stop before you're dead. You can't be dead if your heart is still beating. That doesn't work. Obviously everybody dies with a heart not beating. And we learnt that early on in medical school. But there are certain conditions for which this is a major problem in relatively young people. So there are conditions here. In this particular group, there's some cardiomyopathies. There's hypertrophic cardiomyopathy, arrhythmogenic cardiomyopathy. And there are some things where you dilate your aorta or aortopathies. And then there's these primary rhythm disturbances, the long QTs, and this is a very rare condition, and we won't mention that again. So you could say, well, why not screen people clinically? Well, athletes are screened clinically, and here we have Fabrice Muombo, and what was he called? That one in Denmark? Not very good at football. And then we have Taylor as well. And these all people who are highly screened, all of them were missed. And, most of people are not being screened at all. So why can't you just do an ECG and an echo? Well, it missed our highly screened population. And the problem with an ECG and an echo, it will miss early disease. And certainly for things like long QT syndrome and Brugada syndrome, it is intermittent. So one day you're completely normal, and the next day you're dead. And, well, hopefully not, but it isn't necessarily that screening will pick it up. And actually, if you do an echocardiogram, you're not going to pick up subtle scarring of your heart, and you have to do an MRI scan. You have to have dye in your MRI to actually pick up the scar. So actually, it's not it's much safer to just have a blood test. So I've mentioned some of the diseases that we're looking at. So probably by far and away the commonest is hypertrophic cardiomyopathy. There was Miles Frost, who was out running, who was found to have hypertrophic cardiomyopathy and has set up a big screening program for this. Dilated cardiomyopathy is where your heart is just like a saggy bag, really. But you're not very good at exercise when you have that, so probably less of a problem. And this is the one that most of the sports people will have. You get an increased risk if you take a lot of exercise. We all think exercise is good, and it is good. I don't want anyone to sort of go away thinking, great, I can now just be a couch potato. Not at all. But actually, if you are crazily sporty and you're doing all these marathons, I always think marathons are mad. I had my daughters doing it. God, it looked awful. But anyway, lots of people seem to love doing that. But it's very bad if you have scarring of your heart. And the long QT, the swimming, particularly you go swimming, and if you go swimming alone and you've got long QT, particularly one, it's very bad indeed. And we mustn't forget the dilatation of the aorta, again, can be bad with these conditions. So one thing we're not doing, and I think it's really important, although we do look at the familial hypercholesterolemia gene, screening for coronary artery disease is really pretty poor genetically. And so we've got very little. There is a few genes that we now look at, and we have the polygenic risk score, but actually we're not very good at it. And so I would thoroughly advise taking a good history for that. So it is very important to have a good family history because actually that can certainly send you in where you should actually look. And once you have found a mutation, you can undertake full cardiac investigations. But as I said, you need often a cardiac MRI scan, which is not a minor investigation. And genetic testing is much more straightforward than doing all the cardiac tests. And we know during COVID, nobody could have an exercise test because it was hugely aerosol generating. So anyone who was trying to order exercise tests was having a crazily difficult time during that time. But there is difficulty in interpreting the genetic tests. And then there is the penetrance of these genes. So if you have a mistake, what is going to happen to you? And lots of time, nothing ever will happen to you. So who should we genetically test? And what should we genetically test? Do we just test everybody for everything? And I think we can't do that because of scaring people. You know, if you're told you're suddenly going to drop dead, it must be terrifying. And that's why I think you really do need to get some sort of sense into, and the risks are small. You know, even if you carry one of these genes, most of the time you are absolutely fine. So again, caution. I think arrhythmogenic cardiomyopathy is very useful because of the genes that you can, and the lifestyle modifications. And the same for hypertrophic cardiomyopathy, and clinical screening is very easy for that. This condition, Brugada syndrome, which a lot of people haven't know about, there's only one gene for that. A dilated cardiomyopathy, you're not normally doing a lot, and most of these don't cause a lot of rhythm problems, so probably less important. And then this patient is a very rare condition, and it normally presents in childhood. And aortopathies, I would advise against doing this because actually clinical screening is better than genetic screening at the present time. So who do we test? Well, young patients have got more to gain, but they've also got more to lose. So if you are a 18-year-old and you want to be a professional footballer and you have one of these tests, do you go on and continue your career because that could be stellar and you're not going to have an effect? Or do you say, well, actually, I think, I'll divert my career and do something different? I don't know what the answer is. But they have got, everything to lose or gain. Older patients, on the other hand, have much less to lose in so much as they're not going to probably take up, professional sportsmanship, and actually if you can give them treatment earlier rather than later. So they have got much less problem about their sort of lifestyle issues, and it can be very helpful to their family. And they're taking a lot of medications often, pros and cons of testing. I am really very cautious. And this is a rapidly changing field, and I would not have been standing here 3 years ago discussing this because I don't think it was fit for purpose. Thank you very much.
So thank you, Tessa. I mean, I think Tessa's illustrated why we do need to sometimes approach with caution, and how it's been valuable to have psychological input into the team. I think that's been very important for us. And in all our roles as geneticists, we are also genetic counsellors in many ways. So I think we can help patients who are considering undertaking this kind of test. So we've talked quite a lot about single gene disorders, but one of the things that Michael has been really passionate about as a GP and has felt this should be really integral to our offering is pharmacogenetics. And so I'm very pleased that he's going to tell us a little more about that. Thank you, Michael.
So just a little bit that Tessa can't get away with everything. There is something genetic there. You wonder who bicycles everywhere in the room. Super. So with respect to, I feel very much really positive about genetics and what it will do to people. So even that person with the Lynch syndrome, their outlook will be 25% better by having had that diagnosis. They will go on to aspirin. It will reduce their chance of getting colon cancer by 40%. The particular patient was given chemotherapy for his bowel cancer. It wasn't the best treatment. If he knew he had Lynch syndrome, he'd have been given immunotherapy. It's absolutely transforming. Yes, it's hard for patients to hear information that is difficult, but if it's done as gently as our experts can do it with their knowledge, we help these patients to improve their lives, and it stops people from dying. So with the example of that BRCA case, BRCA1 was discovered in 1994, BRCA2 was discovered in 1995. The patient had their problem just before that. And so as they went to medical family, they never knew, and the lady never had her genes tested until she developed ovarian cancer. That's a death that could be saved. And we've got to really move on this. I mean, the sooner this all takes off, the better. Otherwise, lives are just going down the drain. We're losing our friends. And there's a real problem with this genetics, which is the public haven't been shared in a logical, clear way what happens and how you do it. And we were taught by our parents not to go into the fortune teller's tent, so nobody goes into it. And this is not like that. We're just doing genes where you can do something about it if you know. Pharmacogenes is a much more straightforward, positive, happy subject. And so we all have our metabolism of drugs controlled by our genes. And that's called pharmacogenetics. And if we look at hospital admissions, something like 7% of hospital admissions are due to drug errors and issues. These could be significantly reduced by people knowing that this patient will need half a dose of that drug. And it's across the board. Or this patient can never have that drug, it may kill them. So pharmacogenetics is really exciting. At the moment we give people drugs just based on them being adult, and that's how you give the antibiotics, and it's just given. But we can be so much more sophisticated. In chemotherapy terms, many people get severe side effects and neuropathy from the drugs. If you know that person doesn't metabolize that drug, so when you give it, they're getting a huge dose, then you can reduce the amount of damage that's done by these drugs and the neuropathies. So pharmacogenetics is a really positive area, and it's going to be very exciting. Essentially, it's going to be on everybody's, you'll have your pharmacogenetics put into the doctor's computer, just like we now have allergies and drug interactions. And they will have your pharmacogenetics, and your prescribing will be according to that. And very cleverly, Veritas are involved in some programs that will help doctors prescribe, because it's not easy to know quite what to do if you're a GP who doesn't spend all their time doing genetics. And this will really make a huge difference to prescribing. So that's what we're interested in. This is just giving an example, this slide, of some of the genes that control different metabolic pathways for drugs like codeine with CYP2D6. And then there's a very common pathway called CYP2C19 gene that controls this area. And it's involved in lots of different drugs. So I'm going to just rush through that. But you can adjust patients' drugs by knowing their genes. Some areas are more definitive and absolutely clear, such as certain psychiatric drugs, that since 2009 there have been algorithms for how to change them. Other areas are less clear, and some of the metabolism of cancer drugs lie in that field. So some of the cancer medicines, you'd probably just get a hint from the genes and think, right, I was on the edge of that one, I'll just slightly adjust that, taking into account they're a poor metabolizer of that drug, so they may receive a larger dose. So with this, everybody in the study gains from pharmaca genes. That's a great thing. So what we learn with our whole genome screening is the massive areas where people are helped. And so I sit in my clinic and I think of all the mistakes and how I've not done so well with many cases. It will reduce the amount of that. There's all sorts of conditions we're so bad at telling, things like hemochromatosis, iron overload. How iron results come through us as GPs is very difficult to interpret. And I'm afraid I know I've got that repeatedly wrong. And I have 2 patients who probably got cancers in their livers, hepatocellular cell carcinoma, which maybe if I'd done better, they'd got onto better treatment, just their blood taken off, they didn't need to get it. We can help so many people. So just talking a little bit stage further, we found a lot of people who had variations in their pharmacogenes. And there's a sort of example is if you have a drug called clopidogrel, if you have a stent or if you have a heart attack, you're likely to be put on 2 agents to stop platelets sticking together. You'll be put onto aspirin and you'll probably be put onto a drug called clopidogrel. But lo and behold, 1 in 50 people will not metabolize clopidogrel. What does that mean? Clopidogrel is a prodrug, so it's given and it's inactive. It doesn't work. So if you don't have the enzyme to metabolize it to active, you're taking a drug that is giving you no protection. So we will have very rare cases where somebody has a stent put in, beautifully done by the doctor and the patient, all teamed together. 6 weeks later, they're having another heart attack. And neither of them will realize it's the fact that that drug didn't work. And there's equally easy. If you knew that, there's a drug called Trazodone or Prazodone. You could have put them on that. They're active right from the word go. So it's just giving you a little example. And other examples of this area are in cancer, there's a drug called DPYD deficiency. And probably, again, 1 to 2% of us have that. And one of the most common drugs we give in cancer is called 5-fluorouracil, which is the backbone of many regimes for conditions like bowel cancer, pancreatic cancer, and many others. But I had my friend and patient. He was incredibly brave. He had esophageal cancer. He was heroic. Everybody knew he was gutsy, brilliant. At work, he'd been admired massively for his determination. And so with our friend, we teamed up together with him. He'd often have lots of ideas. And say for his surgery, everybody been meticulous. He had a wonderful operation by George Hanna. He was prepared by Vias Markides, had a pacemaker before. Such dedication. And then he came to his chemotherapy afterwards. So he's got a very difficult neurological condition to manage at the same time. And all of a sudden, he has his first dose. And a day later, I hear he's in ITU. And Robert's there for 7 days. And finally, his abdomen's massively distended. Nobody quite knows what's going on anyway. He gradually settles, and the oncologist rings me up and says, well, I'm sorry, I'm never giving him any more chemotherapy again. And Robert gradually recovers and is very cross and rings me up and saying, I'm wanting a Herceptin, please, or please give me this next drug, please. And I say, I don't think it's going to be very difficult. Anyway, quietly in the background, he's tested for DPYD deficiency, and there he has it. So he couldn't metabolize that drug. So when he was given it, he got an absolute thwack that pretty well killed him. And so this is the knowing your genome means you can avoid these type of disasters. Thank you very much.
Thank you, Michael. And I'm going to invite Ros back to talk a little bit about research, and in a particular polygenic risk. We've talked a lot about high-risk single genes, but this is the other aspect of the whole genome results that we're looking at. So,
the reason we put these talks into sections was to show you that if we do the whole genome project and we sequence your whole genome, we're going to hopefully find things like the mutation like Angelina Jolie had, like Gabby showed you, people at higher risk of cancer, and particularly if we do panels as well, which is how we do the project, where we do actually a lot of genes twice, then we have a higher chance of finding things, but they're relatively rare. So if we so to show you the things that are common, which is the way that genetics is going, and to do this, you do detect these types of variants by doing the whole genome. Then I'm going to use an illustration. And this, again, is the picture of the men lined up in the field by height. So what I'd like to do is, for those men or women in the audience who are over 6 foot, could you just stand up, please? Okay, so this hopefully illustrates for you what we're doing in research. So about 20% of the room stood up. Now, in fact, the things that control your height are not only what you eat, if you eat a good diet, but also huge variations across the genome. So in all of those 3 billion letters, you've got at each point of the letters of the genome. So if you imagine it's like the book of life, when you look at each point in words in the genome, some of you have some letters and some have others, and that can determine whether you stood up or not. And some of these letters actually are also associated with increased cancer risk. So if you imagine that it wasn't now height, but say it was prostate cancer risk, which is what we do in research, I can already take a spit test from everybody in this room, and I can tell you who would stand up. So who would be in that top 20% of the level of risk? And that's where a lot of our research at the Institute of Cancer Research in the Royal Marsden is going. And the thing about whole genome is that you get all the letters of the genome. So we can actually, from that whole genome test, actually find out what that risk level is. So as we saw at the beginning of the talk, we've got the rarer high-risk genes, and there are single alterations in a word, in a chapter, that give you a higher risk. And for your children, generally, it would be a 1 in 2 chance they would inherit that alteration. What's very exciting about genetics and is coming along, particularly in the research area, and it will come into healthcare, I think, within the next couple of years, is what we call polygenic risk scores. So in other words, variations across the genome that tell you what your score is from these variants that are all the way across the book of life. And just like those people that just stood up, we therefore can test these variants across the genome and can find the top 20% of level of risk for breast cancer, ovarian cancer in certain cases, although many of them are due to the rarer ones, colon cancer, and increasingly now cardiovascular risk, although that's very much less well developed. And for prostate cancer, this has been a huge area of research with dramatic developments. And Declan Carhill, sitting in the front row here, we work closely with Declan at the Marsden in what we call a prostate risk clinic. And we are identifying people from these saliva-based type studies, finding out who the people are in the top 20 and 10% of the risk score. And then Declan very kindly biopsies their prostate. And I can tell you, we are already finding a higher proportion of high-risk disease that does need treating. We don't yet have the final results, but this is where the research is going. So instead of PSA testing absolutely everybody in the whole population, which detects often a lot of things that lead to biopsies that don't lead to significant disease, now being able to concentrate our screening into those people who actually are at higher risk, equivalent to the people that stood up. And how do we find these variants? So as Michael mentioned at the beginning, we do large amounts of international research. We spend most of our life on Zoom calls at 9 p.m. because that's the only way you can talk to Australia and America all at the same time. And we couldn't do this work without everyone working together. So it's very important to say we are not a silo. And the other thing is the whole genome project, as you've heard from the fact that we've had several people talking tonight, has not been just one person. And then just to show you what we're currently doing, we're doing a study called the Barcode 1 study. So that's with now 50 general practices across London. This is in the NHS. It is research at the moment, but they give people, men over 55, are giving a saliva spit sample. We're testing them for these variants in the genome that you can see here, whether they've got certain letters at certain parts of the genome, and then they go to Declan's clinic for biopsy if they are in the top 10% of the risk. So in other words, half, the very, very tallest of those people that stood up. And at the Marsden Clinic, if you are at a very, very high risk from these scores, so you can see here, this would be somebody who's maybe in the top 1%, so the very, very tallest person that stood up just now, if it was a prostate cancer risk. And you can see that their lifetime risk of prostate cancer is about 60%. That means that 2 out of 3 of those people will get prostate cancer. And Declan's biopsies have shown us that often they're very aggressive and they do need early treatment. And that's how we've been working together with our colleagues at the Marsden. And then finally, I just want to illustrate a couple of cases where we found answers within the whole genome study. So the thing about whole genome sequencing is that you get the rarer alterations often, but you also get the whole genome. So you can look at letters in the genome, throughout the genome, and look to see what somebody's so-called polygenic risk score is, because each letter that's altered confers a little bit of risk, but a bit like that hand of cards, you add up all the points and you can get quite a substantial risk of disease. And this is an example of somebody here who was in what we call the 98th percentile. That means that this person is in the top 2% of people in the room. So if this was a height test, they'd be in the top 2% of people that stood up. And so this particular person is in the 98th percentile, or if there are 100 men there, he's in the top 98% of the risk level for prostate cancer. And this gives you an idea of the table of results that somebody in my lab has created. And I'm going to illustrate 2 cases. So when you look at these people's polygenic risk score, this person here is in the top 99% of the level of risk. And this person had colon cancer very young, under the age of 35. And we did gene testing in this individual. They had a genetic alteration that you sometimes see in the Jewish population, but it only increased his risk about a small amount. It didn't really explain why he'd had the disease so young. But when we got the polygenic risk score, we realized he was nearly at 4-fold risk compared with the average of the population. And we also think now these variants interact with the rarer variants. The whole genome is really quite complicated. And that's really why I think you do need a genetic group to try and advise you if you're going to do genetic testing, you're going to go in this area. This is not just simple results coming out of a computer. And in this individual, the genetic variants were interacting with this other more subtle variant to give him that large risk. Now that's very important because the subtle variants across the genome are shuffled like a pack of cards every time you have children. So your child may not be as high a risk as you are. And here is the second case, the one I just showed you. He's the man with a very high risk of prostate cancer. And he has very minimal family history. I could find no other genetic variation in him when I did a normal genetic test. And he's going to biopsy next week. And that man has an MRI that's been taxing us for actually about a year. He's got an MRI picture of his prostate, which isn't definitely Bond or abnormal. But we know from our early research that people in this category with the higher risk from these variants are much more likely to have disease on biopsy. So this is starting to alter what we're doing to patients, but only in the research setting at the moment. But watch this space, because I think this is coming within the next couple of years easily for clinical care and screening of populations. Thank you.
So we've talked a lot about the clinical aspects of whole genome sequencing, but obviously we couldn't do this without a laboratory and a company to provide us with the sequence. And when Ros and Michael set this up, they gave this very, very careful consideration as to who would be best placed to provide us with this service. And I'm delighted that Matthew Dixon from Veritas is able to join us just to briefly introduce the laboratory aspects. Thank you, Matthew.
Thank you. I'm here we wanted to give some insight into where we came from as a company, who we are, and the evolution of the service that we provide, and is supported by this amazing team. And I guess, obviously, I want to say thank you for organizing this event. And it's, after all those Zoom calls over the last 2 years, I'm prepared for this. So anyhow, let's go into the history of Veritas. And as you see, far end, 2005, is it 5? Yes, 2005. First genome was sequenced. It's more or less 20 years that Ross referred to earlier. And it was led by George Church in the George Church lab at Harvard. And if you move over to 2014, you'll see that George Church was one of the founders of Veritas. It was a group of innovative individuals coming out of Harvard and the George Church lab that decided, well, we can make this reality and bring it to the masses and make it a type of procedure or medicine that really improves people's lives. And that began the journey. And you see that the evolution of developing the system, developing the analysis, and then it brought us over to where in 2018 is when they were looking for partners to be type of the commercial engine for these services and the brand. And that's when they were able to come to agreement with our founders, which is, I'll give you a little more insight into them in a minute. And we launched Veritas Intercontinental, which we focused in Europe, Latin America, and some other parts of the world. And that led us to this amazing partnership that we have now. And you see that we slowly gotten here. It feels slow, but it hasn't been really evolved. And I think one thing is to have the study, one thing is to have the analysis, but the advancements you make once you start to put it into action, and you realize what it has and what it doesn't have, and that's what we've done over the last 2 years with this team. We've really improved, and we're on the right path. So if I didn't use my okay, so I see some other things. And the important thing is also that we started our production in our labs in Europe, which is key, as we know, data protection, whatever else, but it also is just the overall process. So we did that, we launched that in 2019, and now we are utilizing our own lab in Barcelona for parts of the study, but everything stays within Europe, and it's done by our Veritas Intercontinental team here. And if I wanted to go into detail about who are the founders, 3 gentlemen, and I'm joined here today by Dr. Luis Izquierdo, who is our Chief Medical Officer. As you see in the top area there, they worked together in SynLab. They spent 10 years there. And while they were there is when they had this idea, this opportunity, and this is where this idea was launched. And then they brought people on like myself who knows, but still questionable, but still I'm here trying to support them. So if you see, Javier de Echeverria is our CEO. He was head of innovation in SynLab, and he's been in this space for 20 years. You see Dr. Segliano, Vincenzo Segliano. He's our chief technical officer. He manages our lab, and he's been a leader in this field for many years. And then you have obviously Dr. Izquierdo, who's our chief medical officer. He was the head of medical genetics in SynLab for Latin America and Iberia. before coming over here, and also has extensive experience in this field. And he is in medical genetics from the University of Glasgow, so he was educated in this part of the world. So yeah, this is our three founders, and from their idea, we're here today. And the other key I wanted to say, and then I'll be finished, is the most important part of this whole aspect and what we've done over the last 2 years is the collaboration. And I think because of the place we are as a company, it's allowed us to really spend the time needed to develop and get to the place where we are now, where we feel comfortable, and we're here and going over these amazing examples and really trying to demonstrate the value of this overall service and how this can really change preventative medicine. And if you see that we, twice a month, we have these extensive calls where we talk about results, we talk about the advancements we can do, we talk about what's not going well, what's going well, and it has allowed us to evolve. And if you see, as I mentioned, special case reviews, and I think that last bullet is really key because it's, we could be, or maybe if we were a larger company, maybe if we were at a different stage, this is our service and this is what you get, and it's not perfect, but there's no way we can modify or adapt, but that's not our approach, and we're smart enough to realize that we can't get to those improvements and those advancements without learning from people who are using this with their patients, and every case expands on our knowledge of what we're doing and how we're able to manage this. And I know that my background is outside of medicine, and I came over from the insurance world, and I had international development experience, and that's why I was kind of involved in this project, or I was involved in this project. But what I've learned from a marketing background is it's really interesting to understand where this is for a normal person. And thank you.
Thank you very much, Matthew. So we just wanted to introduce our future plans at this stage. So we've talked about the whole genome screen, but actually what we would also like to do, and I know Michael is also really passionate about, is introducing perhaps a slightly more accessible, lower cost susceptibility panel offering with a particular focus on common cancers, so high-risk genes for common cancers. And also in development, including in that, is a polygenic risk score, as Ros has illustrated, in terms of prostate cancer, but we can also use that for other cancers such as breast and ovary. And so that is something that we are planning to introduce over the next couple of months or so. And Gabby talked earlier about the 84 gene cancer susceptibility panel. And this is something that we are looking to develop with Veritas, because the technology that they would use would not only allow us just to look at cancer susceptibility genes, but other useful genes for which we have an intervention. And so Tessa's talked a little bit about familial hypercholesterolemia, and again, that was something that we would like very much to introduce into that panel. And hemochromatosis and alpha-1 antitrypsin deficiency, as well as polygenic risk score. And it may be over time we could expand that to include cardiac susceptibility genes and other genes where, as we've said already, we feel it's very important that there is a useful intervention if we do this testing. So that's really just some highlights that we hope will be forthcoming in the next couple of months. We're really working very hard on developing those. And I'd like to say thank you. Obviously to Michael and Ros, who've been instrumental in setting this up, and also to our funders who are listed there, and they funded our pilot project, which allowed us to take this forward. So thank you, and thank you all for listening. Michael, I think you'd like to sum up by taking a holistic view of this. Do you want to come and talk about the next generation medical?
I think we've probably all got quite a feel of things, but I suppose what we're saying is, as a GP, if you have a patient who gets colon cancer and you've never recommended them to have a colonoscopy, you feel you've let them down, because colonoscopies stop 70% of colon cancer. And so when we think about screening, we all know lifestyle, what our weight is, whether we smoke, whether we exercise, all these crucial things. That comes first in doing well for our health. But I'm pretty sure that whole genome screening now comes below that in second place. So that will make the biggest change. We can ask Ros, how much will it change cancer mortality? And I often do. And it can vary between 10 and 20%, depending on the weather. I'm teasing a bit. So colonoscopy screening, absolutely crucial, and we're all bad at doing it. I have to be very honest, I've only just done my first colonoscopy. How incredibly stupid. And, you know, we need to think, why was I so stupid? Then, if we move on to cardiovascular screening, there's a major difference we can make in this area. Obviously, so I deeply respect and taking people's blood pressure and whatever tests you decide to do. Mammography will make quite a big difference, and cervical cancer screening, and there's obviously prostate cancer screening. So there's all these different options, but I'm just saying I've always had a pretty high priority for getting colonoscopies on people, but now whole genome screening is my number one. So that's a very big deal. So what we're going to want to do now is just have a brief question and answer session, because we have some fantastic doctors in the audience and a super audience with just some questions. So we're just going to move the question sheets up here, and then just very quickly for 10 minutes, you can ask the questions or thoughts you want to do, and then it's back to drinking. Thank you.